generally seeing that our model, which is a function of predictors, and adding additional predictors, is generally the easiest way to do it is by changing the design matrix, so providing it with columns of certain parameters corresponding to me. Of course, the problem is that choose parameters. These are difficult problems. You can use some, for example, model selection algorithms to select which model is the best for our data set, using, for example, Pareto smooth importance sampling, which we mentioned in one of the video lectures. And generally, we can represent our results in the matrix notation, which should be known to you that our means are corresponding to the intercept and the linear combination of predictors, and with coefficients hidden in the vector beta. The X is a standard notation for design matrix. So generally, we can put more complications in the design matrix. Those are described in multiple books, for example, in statistical rethinking, or in both Gell-Mann books on regression, or in BDA, that really or in multiple courses on Coursera, you can use many functions of linear predictors and put them into your linear model. You can use all kinds of functions. You just put them, evaluate the values for your data set, the set of independent variables, and put them into the design matrix. We have used polynomials as an option. We are not talking interactions because it's a broad topic, and generally it means that it's the best working for binary variables. For linear variables, the justification might be sketchy because generally, as a predictor, you add a multiplication of two predictors. And with a binary variable, that means that what will you do if the binary variable was present or not? For example, male, female. What would you do? And this is easy to interpret. If you have two continuous predictors, their multiplication is, you have to have good reason to put it as a predictor here, except that it works. Because if something works, again, this might be an issue. But here we are focused on different kind of models, so we can see that it can be more complicated, because you can create your design matrix using, for example, B-spline functions. So you can get more complication in your model without limiting yourselves to the elementary functions. So what are B-splines? B-splines are so-called basis spline functions, which are defined by the knots, and generally this is a universal method of approximating functions, that we approximate function as a sum of functions that are zero outside a certain interval. For example, in this case, it will be interval of 0 to 4, for which we have defined 4 basic cardinal basis functions that are representing our result. So those functions are limited to 0, and their combination will be on sum of multiple intervals. So we'll be adding those functions together wherever they exist. So if function is limited, for example, to 4 subintervals, if we have 10 intervals, we just move it around. So generally, spline functions are limited to certain intervals. They give you the smoothness up to a certain degree, so it doesn't have infinite number of derivatives like polynomials do. They have limited number of derivatives, and they are very easy to use in order to approximate the multiple kind of functions, at least up to a certain level of precision and smoothness. Splines are defined by knots, so if you have 4 knots here, you can define those functions that are behaving here as a sum of those functions that you can generally. It means, in a sense, it means that all those splines are on each of the intervals of the consideration, you will have the function can be represented as a third order polynomial. For example, if you are using polynomial plane basis. And it comes from this summing of those functions here. If you have third order base, so you have 4 functions adding to each, from 0 to third order adding to each other on each subinterval. Because all outside of those intervals, you don't have a situation of having more of them. And generally, we locate our nodes in the area of interest. There are methods of choosing that. And as I said, the functions are non-zero on, for example, on 4 nodes and 0 outside of them. So for each subinterval, you have only 4 functions working in each interval, and their sum is a third order polynomial. And on the edges, you need to repeat them, losing additionally differentiability. And what is very nice in this situation is that generally you are modeling the entire function, which is defined on the entire interval as a sum of those base functions. But each of those base functions works only on a very limited scope of the entire function. So we have sparsity here. First parameters work on only one end of the interval, later parameters work in the middle, and so like that. So this is very similar to regression because B-splines are our predictor, can be considered as our predictors, because using them on the independent variable, you get the functions of this independent variable, and you can use them as elements of the design matrix. And the question is how to select nodes. And you have there are multiple situations. If we have evenly distributed samples, not in the sense that you do not have these more samples for a certain point of an interval and less on the interval. For example, you have more samples for the uneven distribution would be like you have a lot of samples on the large values and very little on the small values. Then there's an uneven distribution. In case if you have everywhere the same, for example, you have multiple time series that you've measured on the fixed interval, uniform grid might be okay. If are not distributed statistically, in statistics, one of the popular options of modeling is locate nodes at the quantiles of samples. So you just use the quantile distribution and give you more nodes in the places where you have more data points. And splines are good because they can capture local behavior better. They can get the localized behavior. For example, a transition can be captured or fault can be captured. Design matrices are generally sparse because the columns of design matrix will be defined for the entire interval consideration, but they are represented only on limited. They are non-zero on limited aspects. So you get a sparse design matrix which can be exploited if you have a large problem. You have a lot of data points. Then maybe it will be useful to use that sparsity in order to get faster matrix inverses and stuff like that. And splines are a special case of Gaussian processes, which hopefully we'll be able to say something later during this course. So generally, design matrix is constructed as a value of spline functions in all the data points we have, but of course for most of them there will be 0 because they are outside of the area. So this is a very easy design matrix, and because it's May, we can use the nice spring topic, which is actually one of the oldest data set that we have. We have the data set of over 1,000 years because in Japan there is a tradition of viewing the blossoming of cherry trees, and it was recorded in multiple records for over 1,000 of years. So we have the oldest data set, we have a lot of samples, and we can observe. So it can be used to observe certain behavior, but again, it's an interesting data set because it's the oldest data set. It is the largest time scale span that we have available on the macro scale and not or like on a human scale, not on the scale of universe. On universe, you can of course get the older data sets, but it's an astronomical problems, not practical ones from our point of view. Okay, so we have the second notebook, which, because the time is running out, I will just move quickly over. The changes here that we are just getting from SciPy interpolate, we are getting B-spline function, and from datetime we're getting datetime objects, B-spline object and datetime object, because they will be used to create design matrix and to convert data dates to sensible values. In case of plotting, we get again data from McElrath's GitHub repository. As you can see, we have the minimal values year 800, maximal value is year 2015, so we have over 1,000 years of observations. We are interested in the day of the year. If this information was missing from our dataset, we are removing those points using the not an A method. And our star model looks like it's generally very simple, because we provided with a Bayesian matrix like in any regression modeling with measurements, number of measurements, in this case number of basis function is generally number of columns in the design matrix. We have a parameters that will be a vector of parameters for each of basis functions, and we compute our transformed parameters vector in a vector way, multiplying the design matrix by the vector of parameters and assigning appropriate priors, in this case setting alpha for 100, so around generally in between April and May, and with appropriate standard deviation with broad coefficients for each of the beta, because generally we don't have any justification of giving any of the basis function more weight than others. In this case, is here, and we get the exponential distribution, so we get of sigma, so we get the uncertainty of average 1 day standard deviation. So we are not analyzing the prior predictive distribution here, especially that we have not much time. Rest is the same as always. We compile our model, and this is our basis function. We get the quantiles of our data points. As you can see, we have more data points later, we have less data points here. We consider 15 nodes on the entire 1,000 year period, and we are assigning appropriate values appropriate values here. Okay, so this will be the basis function. Our value is of course day of the year. The day of the year that's of the value we are interested in is on which day of the year our cherries were blossoming. So we have less information on the older days, we have more information now, so here denser our basis function so are denser. So this are the elements of our design matrix. As you can see, they are 0 outside of first few nodes for each of those. So we provide the data set from our spline matrix. We provide outputs of values of the day of the year, which was like, that's why we've limited to only to existing values, and we are sampling it with the with stan. So we get values of our parameters. As you can see, the spreads are differing here. They are not necessarily very symmetric always, but you get those parameters. We are not plotting them because that would be a bit complicated, but we can again consider the mean regression. As you can see, this is a linear model which models a nonlinear function, so there is no issue with that. This mean regression, you get these spline functions. You have a ribbon plot of the mean. So we estimated the mean, and we see how it looks like, and adding the uncertainty of it. So we have a prior predictive, posterior predictive distribution we have around the same mean, we have the uncertainty where the data points are located. And as you can see, our model works better, especially in the end. But of course, not all the samples are again captured. But the model also is very simple, so maybe there are some additional justification of modifying it. Okay, this is it for today regarding new content. Are there any questions for all the 4 people that are listening here, which I'm very grateful for hanging with me through this entire experience? Are there any questions? Okay, I'm assume that there are not any. However, there's one thing more which I can now switch to Polish at the moment to communicate to you. Proszę Państwa, dla ewentualnie zainteresowanych, jesteście teraz na tym ostatnim semestrze, znaczy na pierwszym semestrze Waszych studiów magisterskich i jest, proszę Państwa, możliwość odbycia czegoś, co się nazywa stażem asystenckim, jeżeli ktoś byłby zainteresowany. U nas w zespole mamy miejsce, moglibyśmy mieć miejsce dla takiej osoby. Idea polega na tym, że to są osoby, które realizują, prowadzą zajęcia, robią badania naukowe, dostają jakieś tam niezbyt duże wynagrodzenie. Tam ich zaangażowanie jest na poziomie do 60 godzin miesięcznie, więc nie jest szczególnie dużo. Natomiast no, może być to ciekawy temat, nie wiem, czy pod kątem rozwoju w pracy magisterskiej, czy zobaczenia, czy nas interesują na przykład studia doktoranckie, coś takiego. Jakby był ktoś zainteresowany, zapraszam. Wyślę jeszcze pewnie jakieś ogłoszenie na Teamsie, na czata. Dziękuję Państwu bardzo i życzę miłego dnia. Again, have a nice day. No questions, so other matters ask me directly otherwise. Thank you very much and goodbye.